We've previously looked at Lewis structures, so this presumes that you have some basic understanding how to draw Lewis structures. And we're going to go into a couple more concepts to do with Lewis structures, what to do if you have an ion, resonance structures, if something is electron deficient or electron rich. So let's run through a couple examples of Lewis structures with these other situations that we haven't seen before. And it's really just a continuation of what we've already talked about. So say we have for example, we have the sulfate ion there, right? And it's a polyatomic ion. So remember when we're drawing the Lewis structure, the first thing we need to do is find out the valence electrons. So we have 1 sulfur and 4 oxygen. Sulfur is going to have 6 electrons. It's in group 6A. Each of the oxygens is also in 6A, so they're going to have 6 valence electrons as well. All right, so we're going to have 5, we're going to have 30 electrons, but we have an overall -2 charge, which means this polyatomic ion has 2 more electrons associated with it other than the ones we would expect. So we're going to add 2 electrons for that -2 charge. And then we have 32 electrons we're trying to find spots for. So if we go through our process, we're going to put sulfur in the middle, connect these 4 oxygens with bonds, and that used up 2, 4, 6, 8 of our electrons. So that leaves us with 24 electrons. And then our next rule is to put them on the terminal atoms. Each of these oxygens can take 6 more electrons around it. And that's our 24 electrons. We have 0 electrons left. So we check this. See, sulfur sees 2, 4, 6, 8 electrons around it. Each oxygen sees 2, 4, 6, 8. So everybody's happy with that arrangement. What we have to do is put this Lewis structure in brackets and then put the 2 minus out here. So when someone looks at this, they know that you have a -2 charge, so you have 32 electrons. Otherwise, they would think we put too many electrons around on this this polyatomic ion. So again, with a polyatomic ion or any kind of ion, you have to add electrons for the negative charge. If we had something with a positive charge, then we would subtract those electrons from our total number of valence electrons. Another thing you might run into is a structure like if we had NO2 minus, so we have another ion, we have a -1 charge, so we need to find our number of electrons. So we have 1 nitrogen, 2 oxygen. Nitrogen's going to be 5 electrons, and we have 6 electrons from this oxygen, 6 from this. So that gives us 17 electrons. We have this -1 charge, so we have to add 1 more electron to account for that. And so now we have 18 electrons to hand out. So we're going to start by putting nitrogen in the middle, connecting it to these oxygens so that there's 2, 4 electrons being used. That leaves us with 14 electrons. So we're going to put them on the terminal atoms first. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12. That leaves us with 2 electrons, then we put them on the central atom. So now we've used all of our electrons, but if we look at this oxygen, it sees 2, 4, 6, 8 electrons around it. This oxygen sees 2, 4, 6, 8, but this nitrogen only sees 2, 4, 6. Right, and so what we have to do is increase the amount of sharing that we have taking place. So we're going to form a double bond by moving this pair inside of here. Right, and since it's an ion, we have to put these brackets around and show this negative charge. So now this nitrogen sees 2, 4, 6, 8. So everybody's happy with that arrangement. But you might ask yourself, well, why is the double bond here and not here? Because both of those oxygen are equivalent. And it's a perfectly good question because those are equivalent. So what we'd have to do is draw another structure here where we have the negative bond on the other side. And this would be how we would draw those resonance structures, saying that it could be in one of these two states. And really what happens is these electrons can be floating kind of in between these two areas. And it's more like instead of having one double bond and one single bond, you really have one and a half bond lengths there. So that'd be a resonance structure. So if there are equivalent things like with that nitrogen and oxygen bond where you have one that's a single and one that's a double, you have to show it in both configurations. Another thing that we haven't talked about yet is some structures have elements that are electron deficient. So boron and beryllium tend to be electron deficient. So boron, if you remember, it's a Lewis dot structure for just it. Showed it had these 3 bonds that it likes to share. And so if you're only sharing 3 electrons or making 3 bonds, you're not going to get 8 in your valence shell. Right, and so, BF3. Right, and so if we have boron and it's bringing us 3 electrons, and we have this fluorine with 7, another fluorine with 7, and another fluorine with 7. That gives us 24 electrons. So we put boron in the center. We connect it to these fluorines. And that used 2, 4, 6 electrons. That leaves us with 18 electrons. They're going to go around the terminal atoms. Each of these fluorine can take 6 more. And that's all 18 electrons. Right? And so this is our final Lewis structure, where boron only has 6 around it. Right? And we haven't really been looking at this very much, but you could also, do this other way where you just draw the Lewis structure of the individual atoms, and then say, well, these are going to connect here, here, and this fluorine has its 7 valence electrons in there, and you end up with that same same structure there. So that's an example of an element that its Lewis structure ends up being electron deficient. There are also ones that are called electron rich. And once you get to the 3rd period of the periodic table, then when we draw these structures, those elements have a d orbital that's right above where their valence electrons are. And so they can expand their octet by putting some electrons up into that d orbital. So let's look at phosphorus pentafluoride. So phosphorus is going to bring in 5 electrons. And each of these fluorines is going to bring in 7. Right, so that gives us, 35, 40 electrons. And so we're going to put phosphorus in the middle, and we're going to attach these fluorines to it, right? And so we use 2, 4, 6, 8, 10 electrons. That leaves us with 30 electrons, and our next step is to put them on the terminal atoms. Each of these fluorines can take 6 more electrons around it. Right, and that's all 30 of our electrons. We have 0 electrons left to share. This phosphorus ends up seeing 2, 4, 6, 8, 10 electrons, so it's what we would call electron rich, because it has those extra electrons in its outer shell.